Welcome to the video on the principles of solar electricity and the photovoltaic effect. We will explain how photons create an electric current, describe the structure of a silicon PV cell, and list the primary factors that influence PV output. The core definition of the photovoltaic effect is the direct conversion of radiant solar energy, or photons, into direct electrical current within a solid semiconductor material. This effect was first observed in 1839 and led to the first practical silicon solar cell in 1954. Not all sunlight generates electricity. A photon must possess sufficient energy to exceed the semiconductor's band gap to successfully break a valence electron free from its atomic orbit. This process is called absorption. Let's look at the anatomy of a crystalline silicon solar cell. Key layers include the glass and anti-reflective coating, the N-type layer, the P-N junction, the P-type base, and the electrical contacts. Pure silicon is a poor conductor. Doping introduces impurities, creating an imbalance of charge carriers. N-type silicon is doped with phosphorus, creating extra free electrons. P-type silicon is doped with boron, creating a deficit of electrons, known as holes. When N-type and P-type silicon meet, free electrons and holes rush to combine, forming the depletion zone. This zone establishes a built-in electric field that acts as a diode, allowing current to flow only in one direction. When a photon strikes the P-N junction, it knocks loose an electron. The built-in electric field forces the electron up to the N side and the hole down to the P side. The electron then flows through an external load, creating direct current electricity. The electrical profile of a PV cell is defined by the current voltage, or IV curve. Key points include the short circuit current, open circuit voltage, and the maximum power point. Systems dynamically load the cell to keep it operating at the MPP for maximum efficiency. Real-world variables dictate system performance. Irradiance, or sunlight intensity, has a proportional and severe impact on current. Cell temperature has an inverse and severe impact on voltage, with higher heat leading to lower efficiency. A single silicon cell produces about 0.5 volts. We scale this up from cells to modules, then to strings, and finally to utility arrays. By wiring cells in series and parallel, we achieve gigawatts of usable grid power.